review lecture 2. We started on conservation of energy principle for closed systems, right? And we define the expression for energy principle for closed systems, which was Q net minus work net equals energy stored in the system, right? And we also said Q net equal to N minus Q out, right? And work net equals work by minus work on. Okay. Power cycle efficiency over N. Right? Well, yes, and the duration cycle efficiency for coefficient of performance, right? In this case, beta work cycle over vice versa. Right? So N over work cycle. Okay. N over work cycle. Right. Today we're going to talk about first law of thermodynamics that we defined last lecture, and we're going to apply those formulas. Q minus work equals delta E on some problems, and we're going to see how do we use those, how do we calculate work, how do we calculate heat, what is energy in that case. Okay, we'll just use in the problem solution. So lecture 3. First law, of thermodynamics and mechanical work of course this is for closed system. Right? As we defined in previous lecture, that energy stored from state 1 to state 2, yeah, equals Q net from state 1 to state 2 minus work net from state 1 to state 2. Okay. And E, stored energy that we have is internal energy plus kinetic energy plus potential energy and other form of energy, but we don't consider that as an energy in thermodynamics for this level. So delta U heat interaction from state 1 to state 2 minus work interaction from state 1 to state 2. In closed systems, we neglect kinetic energy difference and potential energy difference. Because in a closed system, medium potential energy difference overall is about the same as negligible. Okay? Since closed system, mass is not allowed to pass through the boundaries. Remember, we defined all these in the first lecture. Kinetic energy difference is zero, so mass is trapped in the system. Okay? So all we have remaining for stored energy is delta U, internal energy. Yes.
And for potential energy, how it changes if the system is really big.
No, it's negligible.
Okay.
So neglecting kinetic energy and potential energy changes on closed system. Okay. Mechanical work. Mechanical work is the result of a force acting through a distance. And we will define what's that distance. And we define mechanical energy difference, right? Delta W equals force applied through that distance S. Okay, S is the distance that the object or the molecules travel. F is the force acting. Okay. We have two forms of mechanical work. First one is expansion. And the second one is compression. Okay. These two are boundary work or mechanical work. In other words, boundary work. So in a closed system, say I have a piston inside closed system, right? Force acting on the surface. Remember how we calculate the work is pressure times volume. Okay? If I multiply and divide distance by area, right, in this equation, if you divide and multiply by area, what you have is pressure times volume. Okay? If you multiply this area times delta S, right, times area will give you volume. And force divided by area will give you pressure. Okay? Force divided by area will give you pressure. Okay? So work equals pressure times the velocity difference from state 1 to state 2. Units, joule, newtons times meter, right? If we multiply and divide by area, typically. Or in US customer units, will be fit times pound force for BTU, right? And 1 BTU equals 778.17 fit by pound force. Work equals pressure times volume difference, right? From state 1 to state 2. Pressure P here is pressure. And we add the volume. Note that W work is equivalent to area under curve and PV diagram. From the definition of integral. An integral is summation of infinitesimally small parts, right? So what we do here is taking a PV diagram and taking the area under the curve, which gives us the work. So work depends not only on the properties of the two and states, but also on the path of two of the processes of the process. Okay. Remember, in the first lecture, we described state 1 and state 2. But we had multiple ways to go from state 1 to state 2, which will give us the behavior of the process. It gives us different calculations. We will see it. Okay? Okay. Example. The gas is compressed from volume 1, 0.09 meter cubed And pressure one bar. 2, volume 2, 0.03 meter cube, and pressure 3 bar. Pressure and volume are related linearly during the process. For the gas, thermal. The work in kilojoules and catch the process line on PV diagram.
Is the V1, is that 0.05 meters?
9.09 meters cube.
Okay.
Pressure 1 bar. In a closed system, you're trying to find what the work is. When I have gas here, and I compress it. So for state one, volume 1 is 0.09 meter cube, and pressure is 1 bar. Okay. And my end state, state 2, is volume 0.03 meter cube, pressure 3 bar. Work equals P dV from state 1 to state 2. Right? State 1 to state 2. Right? You're asked to sketch PV diagram. The PV diagram, right? Pressure. In this case, is meter cubed, and pressure is bar. It is stated in the problem statement. It says pressure and volume are related linearly, meaning that the path of the process is linear. Okay, increment is linear. Okay. State 2 and state 1. Okay. State 2, state 1. Direction of the process. Where's my state 1? Pressure 1 bar. Pressure 2 bar. 1, 2. 0.09, 0.03. Okay, so both meet. This is my compression work. Okay, area under the pressure. Let's calculate that. You can even either take the integration, solve this integration to calculate the area under the curve to find the work, or you can use geometry, right? Rectangle, triangle. I know the height, I know the base, you can calculate it either way. But in the future, this shape will get curvy, not linear, which is usually the case in real applications. But recommend you to use integration, which will be mathematical solution, not as logical as this geometrical solution, but it will give you always right answer. Okay? Yeah. The work pressure delta V dV average times volume difference. Okay. In this case, I can take pressure, average pressure, because my process is linear. Right? I know where my middle point is on a linear process. Right? But I cannot do that. The process is not linear. Perfectly. The average V1 plus V2 over 2. Okay, it will be 2 bar. Right? 1 plus 3 over 2. The work, the 2 bar. Right? My pressure, the constant I can take off from the integral and take care of the rest from state 1 to state 2. Delta volume from state 2 to state 1, lower with V2 minus V1, right? V2. So will give us work is minus 0.12 bar times meter cube. Okay?
Wouldn't the average be 3/2? If P1 plus P2 is 3, right?
Pressure is 1 bar and 3 bar.
Oh,
Have you done? You're asked to calculate the work in kilojoules. Right? I need a unit conversion. The answer I have is not in unit requested in the problem. So we need unit conversions. Okay. Make a small note here. 1 Pascal. equals Newton over meter squared, right? 1 bar equals 100 kilopascal, right? And joule equals Newton times meter. Okay? Work is minus 0.12 per meter cubed. Okay? 1 Pascal times root 5 Newton per meter squared for 1 bar times 1 joule per Newton times meter and 1 kilojoule and to the power of 3. Okay? Which will be equal to minus 12 kilojoules. Okay? To cancel out, bar cancel out, meter, meter square, meter cube, when I had a kilojoule left. Okay? Four. Another example. Here is contract and a piston cylinder assembly from an initial state where pressure 1 equals 30 pound force or inch squared and volume, let's say 25 cubic feet. The relationship between pressure and volume during the process is pressure times volume to the power of 1.4 constant equals constant. The work is minus 62 BTU for us to determine final fluidity. The final pressure in pound force per meter squared. And sketch the process line on a PV diagram. Let's draw a distance in the resemblance. In this problem, I know my work. And I'm asked to calculate the final volume of final pressure. And the initial state, P1, V1, the power of 4 equals constant. Let's call that constant C. State 1, pressure is 30 pounds meter squared, volume is 25. P, pressure 2, no, but volume, that's state 2, 100. I know how to find my work, right? P dV from state 1 to state 2. And the problem, I know the relation between pressure and volume, which is P V to the power of 1.4 of constant. If I take that and put it in my interval, I know the relation. Let's see what happens. Okay? The work, so knowing P V constant, right? Work equals C state 1 to state 2 to minus 1.4 dV. Okay. Okay. Just replace P pressure with this equation. Okay. I took the C out, but it's constant. You want to keep it inside integral. Take it outside. The inverse of P to the power of 1.4 will be minus 1, right? 1.4. And what we have is work equals constant integration from state 1 to state 2. Volume to the power of minus 1.4 dV. Right. If I integrate what I had, work equals constant, right? Minus 1 over 0.4 volume to the power of minus 1. Where the C equals P1, P1 to the power of 1.4. I know my P1, I know my V1, I can calculate my C. Constant, right? Let's calculate that. Equals 30 psi 25 to the heat power of 1.4 for 2,718 psi heat to the power of 4.2. And work is given as minus 62 BTU, minus 62 BTU, primary to unit conversion, 778 feet pound force over BT. It will be equal to minus 48,240 feet pound force. Now I know my work in the units that I can use to calculate my pressure and volume. Work equals minus 48,240 big pound force equals 2,118 pounds, right? Pound force times 4.2, 114 feet squared over feet squared times squared. This times volume. V2 minus 0.4 minus 25 feet squared minus 0.4 times. This times volume. This is integration of what? Okay. Let's solve this for volume 2. So you should find volume 2 to the power of minus 0.4 should be equal to 0.325. And V2 will be 16.6. So P1 V1 should equal to P2 V2. The work is to be calculated either by using state 1 property or either state 2 property, which makes state 1 property relationship equals to state 2 property. Right? P1 V1 equals P2 V2 is the expression we are given in the problem. Right? If you follow that, P2 and P1 times P1 over V2, the power of 1.4. Okay. What I did is P1 V1 to the power of 1.4 equals P2 V2 to the power of 1.4. Equal 30 pound force squared times, I know my V1, right? 25 feet over, I just calculated my P2, 16.6 feet, the power of 1.4 equals 53.3 let's show this on a PV diagram. PV diagram. PV and 4 over P squared. Point state 1 to state 2. Right? The polytropic process and the relation P we found. So in this case, it's not linear. So calculating curve under the area should be by using integration. Right? All right. Another example problem. Gas expands from an initial state where pressure 1 equals 500 kilopascal and volume 0.1 meter cubed to the final state where pressure 100 kilopascal. The relationship between pressure and volume during the process is P the constant. Sketch the process on PV diagram and determine work in kilojoules. Okay. Can we have a closed system? The constant design as expansion. And we will calculate work. In state 1, pressure 500 kilopascal volume equals 0.1 meter cube. State 2, pressure 100 kilopascal. Cube. Pressure in kilopascal. And now it goes from state 1 to state 2. I don't know the path. Is it linear? Is it? Yes? Let's find out. I will come back and draw the 3D diagram at the end of the problem after proving what the path is like. Work. The work, E times integration of pressure and volume from state 1 to state 2. But PV equals constant, okay? Which makes P C over volume. That's what that any size integration. Okay? Work will be, okay. Therefore, work will be equal to constant over volume and delta volume. What is the integration of C over V? From state 1, state 2. Natural log of V, right? V over C1. Okay. From a relationship constant equals P1 V1, which is equal to P2 V2 in this for this particular question. Okay. Work I just found equals constant, which is P1 V1, right? That's natural log of V2 over V1 or P1 over P2. Right? Okay. And then V2 over V1 equals V1 over P2. P1 V1 500 kilopascal times 0.1 meter cube. Natural log of 500 kilopascal over 100 kilopascal. Work equals 80.5 kilopascal times meter cube. But but we are asked to find in kilojoules. Right? So we need to convert the unit work equals 8.5 kilopascal meter cube. And it's about 3 Newton over meter squared kilopascal. 1 joule equals Newton times meter. And 132 equals 1,000. Here, work will be 80.5. If you go back to our PV diagram, state 1 to state 2. Just prove that it's not linear. It's a function of initial law, which doesn't behave linearly. Right? So, and make sure you show the direction of the path. Okay, P, V. Oh. Okay. Under the curve. Look. It's a little strange. Polytropic process. The problems, the relationship we define and given in the problem statement are a typical expression for a polytropic process. For polytropic process, a process which may be described by a process line equation of the form P V power of n equals constant. Is called a polytropic. Work and polytropic process. Work from state 1 to state 2 equal P state 1 to state 2 V minus n PV. integration and eliminate C constant, what we will have by integration and eliminating constant. Work will be V2, V2 minus work P1, V1, or 1 minus X. For all values of n, except one, right? Which makes it denominator 0. If n not equal to 1, so P equals P2, P2 minus P1, P1 over 1 minus n. If n equals 1, what will be, right? We just proved in the last example, P1, P1, which will log off P2 over V1, or P2, V2, natural log of V2 over V1. Okay. Talk about a little bit of rate. Next, both SI and the customer units. For your customer units, right, it will be count force versus count, right? Count. For Newton's second law, weight will be mass times gravity. US customer units, systems, is force, length, and time. system in which the fundamental uniform F in this case contours L P is the US customer units system mass is a dry unit. We choose mass define such that one part mass is the mass of an object which weighs one pound force under normal acceleration of gravity. So therefore, from a Newton second law, one pound force is equal to one pound mass times gravity. The gravity in this case will be one pound force over one pound mass. So this gravity equals pound force over pound mass will be compared to the similar value gravity equals 32.2 per second squared. And this leads a different value for the customer units. You convert pound force to one slag times the squared. And one slag equals 32.2 pound mass. let's perform similar process in SI unit for comparison, where mass is the fundamental unit and force is the derived unit. By definition, 1 Newton equals 1 kilogram meter per second squared. Weight in the case will be mass times gravity. Let's say I have 1 kilogram. Gravity 9.8 approximately. Meter per second squared, and it will be 9.8 Newton. From which we may conclude gravity is 9.8 Newton per kilogram, which equals 9.8 meters per second squared. I know you know all these, keep that in mind. Okay. Any questions? Okay. We can stop here. Okay. That's all for today. I will see you on Thursday. If you have any questions, I will be here. Have a good one.